Section S7, we're going to continue talking about some voltage stability curves, and now we're going to talk about the QV curve calculation. So now we're going to be plotting a curve of the reactive power versus voltage. The voltage stability studies for QV studies how variations in reactive power affects the voltage in the system. The relationship shows the sensitivity and variation of bus voltages with respect to reactive power injections or absorptions. A system is considered voltage stable if a VQ sensitivity is positive for every bus, and voltage unstable if a VQ sensitivity is negative for at least one bus. All control systems, transformers, taps, generator VARs, etc., assume that increasing VARs will increase voltage. So therefore, if we have a negative VQ sensitivity, then that means the assumption is wrong, and the control systems will behave incorrectly and cause the system to collapse because they will keep increasing their VAR injection or changing taps and driving the voltage in the wrong direction. So that's why it's important that we have all positive VQ sensitivities. In order to create a QV curve, what we do is we insert a fictitious generator at the bus that's being analyzed. The voltage set point of the generator is then varied, and its VAR output is allowed to be any value needed to meet the voltage set point. The vertical axis depicts the output of the fictitious generator in megavars, and the horizontal axis depicts the respective voltage under this condition. The base case operating point of the system is represented by the x-intercept of the curve. This is the point where the fictitious generator is at 0 megavar output, or in other words, the base case condition. As you trace the curve down, it represents a decrease in the fictitious generator's megavar output, which represents an increase in megavar load. So what we're really doing is we're increasing the megavar load demand. And therefore, as you can imagine, if you're increasing the VAR load, your voltage should be going down. So the curve is thus tracing what the voltage would be as you increase the load megavar and decrease voltage. At some point, the megavar value of the generator will stop decreasing and reach the bottom of the curve. This point represents the maximum increase in load megavar at the bus. Any higher value of megavar load at the bus and a voltage collapse would occur. So this is an example of a QV curve. So we actually plot the VQ, if you want to get technical, because V is the x-axis and Q is the y-axis, but we still call it a QV plot. The most important value is the minimum Q megavar down here. This is the amount of VAR load that we could have before we have a voltage collapse if the VAR load gets any higher than that at that particular bus. Over here we have our base case operating point where it's crossing the x-axis and what the voltage was at that point. So this is our base case voltage right here, somewhere between 1 and 1.1, probably around 1.03 or 1.04. So this is what our curve looks like, and this is the value we're interested in right here, which is how much VAR load could we add before we experience a collapse of voltage. Note that it's sometimes possible to plot a curve where the curve does not cross the x-axis. This means the system cannot solve this case. There's no base case operating point, and you need more megavars to come out of collapse. So this tells me here, this number here tells me how much VARs would I have to increase in terms of generation, how much would I have to inject. Instead of taking load out here, this is how much load would I add before I get to the collapse point. This is telling me I'm already past it. So how much VARs would I have to put back into the system with a generator to even get to this point? So I could bring this down to 0 by adding in about 70 megavars roughly, would shift this curve down to where the base case operating point would be right at the critical point. If I want to actually get it up here to say 1.0 per unit and shift this curve all the way down so that my base case point becomes right here at 1 per unit, I would have to add in about 175 megavars to make it a reasonable per unit voltage under the base case. So that's how you can kind of read one of these curves and make a determination perhaps of what do I possibly need for VAR support at a bus like this if I have a condition where the voltage is low under whatever my current system state is, and I want to bring the voltage up, which is the equivalent of shifting this curve down by adding in some amount of megavar support from either a generator or a shunt device. Like up here, we plotted out only so far. We'll see in the options you can specify how far out it goes. There are times when, if you notice, when you have a system where you've got low voltage sometimes, somewhere else in the system you often have really high voltage that corresponds to it. So I suppose you could look at that and say, well, if I've got a really high voltage going on at a bus somewhere, that probably means I've got some really low voltages going on somewhere else. But generally what we're looking for is the knee of this curve down here and where that's occurring and how far above or below the x-axis does that happen. PV and QV curves require selection of specific buses for analysis. So just like we had to specify what we wanted to monitor for the PV, we have to do the same thing for the QV. We need to specify where we want to calculate the QV curves. Unless a known problem exists, the selection of buses could exclude problem buses. So VQ sensitivities can provide a more system-wide view of stability and can help you determine where you might want to plot the QV curves. So VQ sensitivities are calculated from a solved power flow solution at a particular operating point. So the sensitivities do depend on your starting system state. They can be calculated much more quickly than a full QV curve. And the sensitivity, the VQ sensitivity of a bus is the slope of its QV curve at the given operating point. So that's why you can use those VQ sensitivities to find locations where those buses or a particular bus might experience a QV problem quicker than another bus. So the VQ sensitivity will indicate stable or unstable operation. We've mentioned before, if it's positive, it indicates a stable system. Smaller positive sensitivities indicates more stable. Negative sensitivities indicate an unstable system, and to maintain stability, expect voltage to increase as VARs are increased, which is the opposite of typically what you expect. Interpreting VQ sensitivities, there's a nonlinearity of the VQ relationship, which makes comparing the magnitudes of sensitivities between different operating points difficult to determine a relative degree of sensitivity. Negative VQ sensitivities can occur at buses near branches that have a negative series reactance. Because of that, you can't always say that a negative VQ sensitivity is necessarily bad. Usually it is, but there are situations where it's acceptable. Those situations are at a fictitious star bus of a 3-winding transformer, because 3-winding transformer equivalent models may have a negative impedance. Buses near series capacitors, because series capacitors have a negative reactance. And we generally ignore these particular negative values, but you have to kind of know that they're negative VQ sensitivities because of one of these situations. If we have a negative VQ sensitivity, you would end up with a QV curve that looks like this, and your base case operating point is actually on the low side of the curve. And so your operating point would be over here on the left. This is not typically what we want, because as you increase Q, you're driving your voltage down instead of up. So that's why we don't like to have negative VQ sensitivities, except for the couple of exceptions we talked about on the last slide. Generally speaking, you want your VQ sensitivities to be positive, so your operating point is on the proper side of the curve. And as you would expect, if you increase the VAR support, you would increase your voltage. This way, if you increase your VAR load, you would decrease your voltage. Over here, if you increase the VAR load down here, your voltage would be going up. So we're going to perform a QV study on a B7 flat case. So we're going to go ahead and open up this B7 flat case, and we're going to modify it by opening a line from bus 5 to 7. So we'll go ahead and do that in Simulator, and so you can see it from there. So we'll go ahead and run Simulator 19, and we're going to open a case. And the case we're going to open is the B7 flat case, which should just be in the training cases folder. So we'll go B7 flat.pwb and open up this case. And we're going to modify this case a little bit. First of all, I see that there's an open line here between 1 and 2, which looks like it's an artifact of a previous example that we were doing, and it got saved that way. I'm going to close that line in and do a single solution. Then I'm going to open the line from 5 to 7 and solve it again, and I should see something like this with a line overload on the line from 2 to 5 of about 115%. So this is the initial condition we're going to use for this QV tool. What we're going to do now is we're going to stress it even further for the analysis by setting up a contingency to take the line from 2 to 5 out because it's overloaded. So we're going to go into the Tools ribbon tab and click on Contingency Analysis and go over to the Contingencies page and right click and do an Insert. And we're going to insert a new element, and the element we're going to insert is of type branch. We go over and select the near bus and the far bus, and we're going to select bus 2 to bus 5. And the action we're going to perform here is we're going to open it. So we just click OK, and we'll now insert a contingency to open line 2 to 5. And I'll go ahead and click OK, and I can give it a name. I can say CTG 2-5, so it's my contingency of line 2 to 5, and it will add it for me, so I now have my contingency defined. So this is the contingency I'm going to use for the QV curve. So now I'm going to go to the QV curve analysis tool, which is an add-on tool again. So I go to the add-ons ribbon tab, and right in the middle in the PV and QV curve section, I'm going to click on my QV curve tool. So I open up the QV curve tool, and the first thing that pops up, you'll notice, is it opens up to a page of buses. Because again, just like in the PV tool, I have to specify which buses I'm going to track or plot voltage for. So on this page, I want to toggle the QV selected column to yes for the buses that I want to analyze. You can also enter the per unit voltage ranges for which you would like to draw the QV curve down here, so you can add those in. Over here for min volt and max volt, you can modify that if you want to limit the minimum and maximum that you want to draw the curve for. In this case, I think what we're going to track are the voltages at buses 3 and buses 5. So we're going to QV selected for 3 and 5. So this is where we're going to be able to plot QV curves for. I can also track actual voltages to store. So I can go to quantities to track over on the left. And just like in the PV, you notice that we had all kinds of different values you could track during the course of the PV or QV calculation. We're going to do that again here. We're going to track, let's say, the voltage and the angle of the buses 3 and 5. So we'll toggle those to yes as well. And what that's going to do is, as it's solving the QV during each iteration of the solution process, it's going to also store the value of the actual voltage and angle, magnitude and angle as well. If we go to the options page here, this is going to set up how it's going to perform the calculation for the QV. The way the QV works is it's going to start at the base case value of voltage, and it's going to start ramping the voltage up first. So it will ramp it up in step sizes of 0.01 per unit, so you can specify the step size of the voltage here. It's going to calculate the VAR injection of the fictitious generator that's needed to support the voltage as it goes up each step. So for each 0.01 per unit increment that the voltage goes up, you'll get a value of Q injected by the fictitious generator needed to maintain that. It'll go up to a maximum value, so it'll go up to whatever you specify here, so you can set it to 1.1. If you want it to go all the way up to 1.4, 1.5, you can change that, and it'll keep going up to that value. Once it hits the maximum, it comes back to the base case and then starts decreasing the voltage by increments of the step size and solving for the Q extracted by the fictitious generator. In other words, you're increasing the Q load at each 0.01 per unit increment, and it will go all the way down to 0.1 per unit. Now, oftentimes you will see that the Newton-Raphson load flow will fail to solve before it gets to this low of a value, but it gives it at least a finite point that you could set it to go no lower than. You might change it to 0.5, you might change it to 0.4, and in some cases the Newton-Raphson is able to get down to a voltage of 0.3, 0.5 or 0.4, so you would have it stop if it gets that low. But if it determines that Newton-Raphson can't solve before it gets to this minimum voltage, it will just stop at that point. It won't obviously keep trying to get to the minimum voltage if it has no way to get there. There's also some global solution options that you can set if you want the solution options to be different for the QV, because it is, again, solving a load flow calculation at each increment of the per unit ramping up or down. So you can change the global options there if you wish. There's also some QV power flow solution options. These are the options that it will use during the QV. I should clarify, these are the base case global solution options. So these are the options that you have set for your load flow, just your basic load flow. You can change some of those options for the QV calculation so that it might use different options when solving the QV than it uses when solving the base case. So right now, if it's a square in each box, it's using the defaults that are defined over here. Or you can toggle one of these to either a check mark, which means it uses the option for the QV always, or you can make it an open square, which means that it will not use that option under the QV regardless of what the global options are set to. The long story short is what you're really doing here is you're just customizing perhaps the solution options for the QV different than what the global options might be set to. You can also choose where you want the QV makeup power. You can choose to have it always made up at the system slack bus, or you can tell it to just use whatever the contingency analysis is set up to use. So if you've defined your contingencies and your contingencies have a specific makeup power source defined, it can use that. If you want it to ignore whatever the contingency makeup power settings are and just use the system slack, you can toggle to do that instead. If we look at the contingencies page, there's not a lot here other than do you want it to include the contingencies or not in running the QV analysis. If you check this box, it will process any contingencies you have defined. You can also tell it to skip the base case calculation and only do the contingency defined calculations if you want. And there's also an option here to attempt to make unsolvable contingencies solvable with a synchronous condenser. What that does is if it tries to run a contingency and it determines that the contingency just fails to solve, it will stick a synchronous condenser in to try and make the contingency solve so that you can get a plot. And then you have to take into account when you look at the plot that there's some additional reactive power that was supplied by this synchronous condenser to make it solve in the first place. And then there's an output option, which is you can save the results to a text file that you can open and look at outside of Simulator if you wish. There's an option to plot the curves as they're computed. And when plotting V versus Q, do you treat Q as the output of the fictitious synchronous condenser that it put in to ramp up and down? Or do you want it to be the total reactive injection at the bus, including shunts but excluding load? Usually we look at just this value right here, which is we're caring about how much more has been added or removed from the bus as it currently stands that moves the voltage up or down for generating the plot. Otherwise, if you just plot this right here, as we mentioned, at the point where the Q is 0, meaning we haven't injected anything from the fictitious synchronous condenser, where it's 0 is where the base case condition exists. That's not as evident if you include this down here because, for example, again, if you have a 50 megavar injection there and you have no injection from the synchronous condenser, where it crosses 0 isn't actually where the base case condition is at that point. We usually default to just plotting the voltage versus the fictitious synchronous condenser injection or extraction. So those are the options that we have to set. There's not a lot of options for the QV. So we can go to results and we can wait and we can go ahead and click run. as I mentioned before, it has plotted some curves as it went. Now, our experience has been that it, for some reason, only plots the base case curves automatically. And I believe the reason is because of the divergence of the contingency at bus 3. It doesn't plot the curves because you'll see that at bus 3, our contingency actually diverged. So we didn't get a plot for that curve, so it didn't plot the contingency curves. But we did plot the base case curves here, and then we'll go look at the contingency curves a little bit separately later on. If I look at this now, I can see that it has plotted my bus 5 and bus 3 curves. So this is base case. I can see that here's my zero crossing for bus 5, for example, is 0.96 per unit. So that was my base case voltage. It went down all the way to about not quite minus 250 megavars, so about a 250 megavar load that it added before we found the nose point of the QV curve at roughly about 0.05 something, 0.052 maybe per unit voltage. So that was the lowest voltage we got here at the nose point. If we look at bus 3 was a lot more stable. It started at a value of about 0.98 and went down, and it took minus 1,000 or 1,000 megavar load to find the critical point under the base case. Now I'm going to close these plots here, and I can right click on one of these result records in here, and I can go to plot QV curve, and it will create a plot of that curve for me. And you'll notice when you create a plot for bus 5, you'll see we get a condition like I explained before where we have no zero crossing of this curve. So again, what that has told us is that in the contingency scenario, we actually had no solution. And that doesn't surprise me, considering that for bus 3, it was even unable to plot it because it diverged. The load flow diverged for bus 3. So not a surprise that for bus 5, we get a plot. It was able to come up with a plot, but it did not cross the zero axis. So it actually is telling us that we had no solution under contingency. We had a voltage collapse under contingency already. I can see that if I was able to inject a little under 20 megavars at bus 5, I could shift this curve down to the zero axis and get a solution point. So I can get this down to crossing the x-axis if I put, for example, 20 megavars in here. And what I like to do in this example is I like to then go out to the curve, and I'm going to go into edit mode, and I'm going to say draw. So I'm going to go to the draw ribbon tab, and under network I can add a device. So I'm going to add a switch shunt at bus 5, and I'm going to leave it fixed, and I'm going to give it a 20 megavar nominal injection. And I'm going to say OK and plug that in. So it puts one in for me. I can go back to run mode. I'm going to do a single solution. Then I'm going to go into the contingency analysis tool, and I'm going to say in the contingency analysis tool I want to set as reference. What this does is it tells simulator to take the modified load flow I just performed after adding the switch shunt and make that the new reference for the contingency analysis. That's a very important step. If I did not do that and I solved the contingencies again, it would solve them without that switch shunt in there because it would have stored the reference case prior to me inserting the shunt. So I'm going to set as reference, and I'm going to say yes, I want to continue and do that. And then I can close it. I don't need to run it right now. I just wanted to set the reference. And now I can go back to my QV curve tool, and I'm going to rerun this. So I'm going to run it again. And if I go again, look at my plot for 5, so I'm going to go ahead and say plot QV curve. I can see that I got closer, but it actually didn't still get to my minimum. And the reason is because I put in a nominal voltage of 20 megavars. But the voltage is still low at this point, that at the actual megavar injection is a function of the voltage. And so therefore, even though I put 20 in, I actually ended up still with slightly less than what I needed to get to the reference point. So instead of shooting for the minimum, I'm going to shoot for something up here instead. So let me shoot for something around 1 per unit, which would be right around in here. And for that, I need to add in maybe another 90 megavars on top of what I've got now. So I'm going to go back out here. I'm going to go to my switch shunt, open the dialog, and I'm going to add in another 90. So let's make this 110 megavars. Click OK. I'm again going to go back to my contingency analysis tool. I'll solve it first. So I'll do a single solution. I'm going to go back to my contingency analysis. So tools, contingency analysis, and I'm going to set the contingency analysis reference to the current case. Now it pops up and asks me that because I've been in the contingency analysis tool before and solved it. So I'm going to say yes, I want to make that my new reference. So I don't have to come down here and do set as reference. I will anyway, just to make doubly sure that I have it set. Close that contingency analysis. Now go back to the QV curve tool and run it again. And now you'll notice bus 3 no longer diverges. Bus 3 now generates a plot under contingency. And bus 5 now has a plot under contingency. So I go ahead and plot bus 5. So right click and plot the curve. And sure enough, I do cross the 0 axis right around 1 per unit with the 110 megavars that I've injected. And now I can see what my curve would look like and where my collapse point is. My collapse point is that if I extract roughly, or take a load of roughly 30 megavars, a little more, that's all, off of what I've currently got in here, that I would reach the nose point of the curve at bus 5 under contingency. I had to put in 110 megavars to get it up to a decent base case solution point, and then I can backtrack and identify that it really only takes a little over 30 megavars of load, or removing 30 megavars of load from the bus before I reach a collapse point. This tells me that for my current system state, under this particular contingency for bus 5, I really do need to have this var injection there to make this a stable system from a voltage security standpoint under this contingency. And now I have bus 3 available that doesn't diverge now, that I can go and plot a curve for bus 3 as well. And I'll see bus 3 really does have a lot more stability than bus 5, but because bus 5 was unviable before, could not be solved, bus 3 didn't even try to solve the QV plot there. It just said it diverged because the load flow failed. So these are the curves that you can generate. You can see how you can use them to try and figure out what VAR injection or extraction perhaps you might need at a particular bus under a certain condition to shift the stability point of that curve up or down. And it's very helpful, like in this example, when I had bus 5 had no solution under contingency, but I could generate a curve for it, that I could use that curve to come up with roughly what I needed to add for VAR support at that bus to help make that bus a viable solution under that contingency. The PV and QV curve tools are very helpful for looking at some of your PV and QV stability issues. Make sure you remember that you can use the VQ sensitivities and the PV sensitivities to help you along the way as well, and understand what the difference is when you have a positive sensitivity versus a negative sensitivity and what that means. But these two tools can be set up fairly quickly, and you do have to have somewhat of an idea of what you're looking for and where you're looking for these values at. but you can specify where you want to plot these, set up your transfers, modify your transfers for the PV based on a particular scenario you're doing, set up contingencies for the QV based on particular contingencies and scenarios you know that cause you problems, and then you can generate these plots to help you identify maximum transfer amounts for PV stability, or QV curves can help you determine reactive power support or injections you might need to help maintain stability from a reactive point of view.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.